Hi everyone, Dr. Malinoski here with a brief video entitled Calculation Help: How to Answer Solution Problems, or How I Learned to Stop Worrying and Love Dimensional Analysis. So this video is going to show you how to recognize a solution problem from the other common types of calculations that you will encounter in this course, and it will help you solve these kinds of problems using a specific method of approach known as, you guessed it, dimensional analysis. Pictured on this slide are three different types of calculation problems, and only one of them is a molar solution problem that would be solved using the method that we will go over in this video. First, just to clarify, what is a molar solution problem anyways? Well, a molar solution is one in which the concentration of the solution is expressed in moles per liter, which is something that you might remember from a previous course in chemistry. Molar solution problems are pretty much always asking you to make a molar solution from a solid. So to make this a bit less abstract, imagine you're in the lab. You have a container with a pure powdered chemical whatever inside of it. To make a molar solution, you're going to need to measure out a certain amount of that chemical to make a solution with a particular volume and concentration, which usually is specified in the problem. So let's start with some rules that will help you identify a molar solution problem. First, I want to warn you about distractors. Note that all three of the problems on this slide list a molecular weight for the chemical. You will need a molecular weight to solve a molar solution problem, but this isn't a good indicator necessarily that you are dealing with a molar solution problem. I mean, this could just be an extra piece of information that's trying to distract you from the actual problem. Sneaky test writers love to include molecular weights everywhere, even when you don't need them to solve the problem at hand. So next, ask yourself if the question is asking you to find a volume or a mass. If the question is asking you to find a volume, like the question in the upper left, this is probably a dilution problem and not a molar solution problem. Dilution problems are solved using a different type of calculation. Finally, if the question is asking you to solve for a mass, see if you can tell what kind of solution it is asking about. In the question on the bottom, the question is asking about a percent solution, weight by volume. You can tell because of the percent symbol. I mean, what the heck is a percent solution anyways? You will find out later in this course, but for now, realize that this is also not a molar solution problem. So that just leaves us with the problem on the upper right, which, yes, is in fact a molar solution problem. It wants to know how many grams, a mass, that you will need to make, let's see, it says it, a molar solution. Alright, so we've identified a question that is in fact a molar solution problem. Great, now what? Well, now we use dimensional analysis. Okay, don't turn off the video yet. I know that dimensional analysis is a scary long term, and I admit most people fall asleep right in the middle of hearing it. There's something about those two words sandwiched together that makes people's brains just turn off immediately. But I promise you, this is the single most helpful method you can learn to help you solve math problems, not only in this course, but in chemistry, physics, biochemistry, really any other course where applied mathematics are used. So what is dimensional analysis anyways? The word dimensional here really just means a unit of measurement, like a mile or a kilometer, or a gram, or a milliliter. And really, all that dimensional analysis means is that you're going to pay attention to and track your units as you're solving a problem. Almost always, when you're trying to solve a calculation problem, you're really just trying to manipulate the information that you've been given to another form. If you look at the units of everything given to you, a lot of times these problems nearly solve themselves. Okay, back to the question at hand. The molar solution problem. How many grams of potassium hydroxide are needed to create 823 milliliters of a 3.7 molar potassium hydroxide solution? So, let's start by taking a look at what we know based on the question itself. We know the molecular weight. Also, we know that we're going to need to make a 3.7 molar potassium hydroxide solution. So, this is the first point where dimensional analysis is going to rear its ugly head. I always write out molarity in terms of moles per liter because this is more useful for keeping track of my units later. In this case, a 3.7 molar solution would have 3.7 moles of potassium hydroxide per 1 liter of the solution. We also know that we are going to want to make 823 milliliters of the requested 3.7 molar solution. Great. So that means now we just have to figure out how much potassium hydroxide we would need in order to make the solution that it's asking about. Just based on what the question is asking, we could start to set up a multiplication. 3.7 moles of potassium hydroxide per 1 liter of solution multiplied by 823 milliliters equals... wait, we can't actually do this calculation. Why not? Well, look at the units. If we actually performed this multiplication, we would end up with units of moles times milliliters per liter. That's not a unit that makes any sense, or at least certainly it's not being simplified in any way, so that should let you know something's wrong. So, by just looking at my units, analyzing them, I realize that this calculation that I'm trying to do isn't quite right. So, if that calculation isn't right, what calculation is? Well, we are on the right track. We do want to know how many moles of potassium hydroxide we would need to make 823 milliliters of a 3.7 molar solution. But what we really need is for some units to cancel out. Since molar solutions are expressed in terms of moles per liter, we would really need the 823 milliliters to be in units of liters so that that will cancel out and leave us with only moles. Now, you could do that conversion of milliliters to liters in your head if you like, but I prefer to write everything out. This way I am really keeping track of my units and I can plainly see if everything is going to cancel out the way that I want it to. So let's set it up. See, all I did was add a conversion factor. In every liter there are 1,000 milliliters, and you can see the way that this calculation is set up. There are units of milliliters and liters in both the numerator and the denominator. As such, the units of milliliters and liters will both cancel out, leaving us with only the units of moles, which is what we want. Now, we're not quite done. We know now that we will need 3.0451 moles of potassium hydroxide to make 823 milliliters of a 3.7 molar solution. But we can't actually measure out moles on a scale. That's just not how moles work. But we could measure out grams. Now, if only there was some sort of term that would allow us to convert between grams and moles. Oh, and there is, right in the problem. The molecular weight of potassium hydroxide is 56.11 grams per mole. Great, let's set up another calculation. But before we set it up though, how do we know if we're supposed to multiply or divide by the molecular weight? Honestly, people often get confused by this and end up with the wrong answer right here at the last step. But once again, if you write the calculation out and you use dimensional analysis to keep track of your units, you see that you have to multiply in order for the units to cancel out properly. If you divided, you would end up with the units of moles squared over grams, and nobody wants that. So if we set up the multiplication, boom, 3.0451 moles times 56.11 grams per mole equals 170.861 grams of potassium hydroxide. This is how much potassium hydroxide we would need to measure out on a scale to make 823 milliliters of a 3.7 molar potassium hydroxide solution. So, I get it. Dimensional analysis is a terrible pair of words, and it probably does seem overcomplicated, but honestly, if you write out your calculations, you write out and you keep track of your units, it really can help you not make simple errors when trying to solve calculation-type problems. I mean, molar solution problems are relatively straightforward, and as you saw in the video, By using dimensional analysis, I was able to avoid two errors that are honestly pretty common and all too easy to make. Anyway, I won't wax on about this any further. That's how you recognize and solve Molar solution type problems. I hope this helped.